Hi guys, today we'll try to understand Thevenin's theorem and how we apply Thevenin's theorem in a network through an example. So in this example, I have taken a question from GATE 2017 in the electronics and communication paper. It was a 2 marks question, and in the question it was asked to calculate the Thevenin's equivalent resistance at node B. But I have tweaked the question and will try to calculate both the Thevenin's voltage and Thevenin's resistance from the following network. So we'll use this equation over here, and this is a generalized equation that can be used to any circuit to deduce the Thevenin's equivalent voltage and resistance. Okay, let's deep dive into the circuit. Let's copy this and okay, so we have copied the circuit. Now let's try to calculate the currents through each of the resistance. So let's first determine the node. So we have a node here, I name it A. We have a node here, I name it B. Okay, let's go one by one. So we see through the 1 ohm resistor we are having a current I naught. But if we take a closer look, we see that the voltage across the 1 ohm resistor is also V test, right? So the current that will be flowing through this is nothing but V test, correct? Now, since I naught and V test are flowing in same direction, and they are flowing through the same branch, so we can say that I naught is nothing but V test. These two currents are same. Now let's move our attention from node B, and we see that we have a dependent source 3 I naught. So the voltage across node B and node A is nothing but 3 I naught, and we know I naught is equals to V test, so this is nothing but 3 V test. Now we are able to calculate the voltage across this resistance 1 ohm. So the current that is flowing through this is nothing but 3 V test. Hope we are able to understand this far. Okay, now we'll apply a KCL over here at node B. Okay, so KCL at node B. Okay, now applying KCL at node B, we see that I test is the incoming current, V test is going out, 3 V test is also going out, and we have another current, let's name it I dash, which is flowing through the dependent source. So that is also outgoing, so we name it as I dash. Now if we deduce this, we get I dash is equals to I test minus 4 V test. So we just point it out in the circuit. So this current is I test minus 4 V test. Okay, now apply KCL at node A. So let's apply KCL at node A. Okay, so for that, first we need to calculate the current that is flowing through this 1 ohm resistor. So as you can see, the voltage across this 1 ohm resistor is 10 volts. So the current that will be flowing through is nothing but 10 amperes, correct? Now let's apply KCL and calculate this current which is flowing through this voltage source. We name it as I double dash. Okay, so I double dash, this is the outgoing current, plus 10 amps should be equal to I test. There's some space constraint, let's put it here, minus 4 V test plus 3 plus 3 V test. So what do we get? Let's write it cleanly over here. 10 amps is equals to I test minus 4 V test plus 3v test. So we get I double dash plus 10 is equals to I test minus v test. Okay, so I double dash is nothing but I test minus v test minus 10. Okay, so we write it over here. This is I test minus 10 minus v test. Okay, now we see this current is incoming, so we apply a KCL over here. So applying KCL at node C, we get I test minus V test minus 10. This is the incoming plus 10. Let's call this current I triple dash is equals to I triple dash. So I triple dash is equals to I test minus V test. Okay, we're good over here. So let's put this current over here. I test minus V test. And at this node, okay, V test is the incoming current, so it will be added to this and we'll get nothing but I test. So we are good over here. We have calculated all the currents in the network. Now we need this expression. We need to copy this circuit. I think this is kind of quite messy, so let's see. So now this was 10 volts, right? And this was V test. Okay, so if we apply a KCL around this outer path, and let's see what happens. So KVL at the outer path. So we'll consider when we are going from negative to positive, there's a potential rise. So we'll consider as a positive voltage over here, over here. But when we are going from positive to negative, we consider that as a potential drop. So we'll take that as a negative and the voltage across the resistance. So let's apply this. So we'll have a rise of 10 volts. If we go like this, then we go like this. So this is plus 3v test. We know I naught is equals to v test. Then this is a potential drop, so minus v test. Correct. I test minus v test is equals to 0. Okay, if we deduce this one, let's reduce this. So this and this minus 2b test, 3b test minus 2b test, will get 10 plus b test. I'll move this to the top, plus I test is equals to 0. So we'll put it in the this form. This will be v test minus I test minus 10. So from here we can see that RTH is nothing but minus 1 ohm and VTH is equals to minus 10 volts. So this is how you analyze a network to determine the Thevenin's equivalent voltage and current through this generalized equation that I've shown over here. And we will be able to deduce any network to Thevenin's equivalent by this example that I have shown over here. I hope this video is helpful. You people were able to understand it clearly. If you have any doubts, any questions, any queries, any confusion, you can post it in the comment section. If you liked this video, if you have understood the concept, please do hit the like button, subscribe to the channel, and keep supporting us. Thank you so much. Signing out. Bye bye.